Sxd Arena project consists of a rugby stadium, which can be also used as a concert hall and of office space. BIM is a comprehensive model that includes all elements of information about the building: technical, structural, dimensional. We started by drawing all the existing elements as well as future construction, such as the future tunnel for the underground line, for example, the ventilation plant with its connection to the A14 motorway. To this, we added all the other elements of the project, such as the foundation. We created a model that you can see here, which is a technical drawing. By technical, we mean that it contains all the structural and dimensional elements. It can be linked to a calculation model, which can be used for summary checks, consolidation and reconciliation controls. After drawing the foundations, we started drawing the structure of the stadium and the office, as well as the turret seating. Over this element, we drew the roof structure. By zooming in the roof structure, one can see as much detail as you can see here. That's the construction drawing phase. We modeled the drawings made by the design office and integrated them into a 3D model to allow for the different analysis. For example, we made some correction to ensure consistency between plans and cross-sections. We also carried out the analysis of the interfaces. In the case of the stadium, for example, we had air handling units in the roof with which we carried out the different analyses and made the adaptation to the structural element accordingly. We also integrated the facade designed by the architects into the model, as well as the concrete shells designed by our offices. The model combines the technical elements designed by our company with the volumes designed by the architects. One of BIM's possible uses is for the metering and follow-up of a project. We were asked to monitor all the elements of the facade over time. These elements are made of a glass and steel, and we were asked to make sure that the architect had integrated in their studies the adaptation and optimization required by the general contractor. With this type of request, the operator can query the model and find all the necessary elements of information: dimensions, surfaces, lengths, arc, angles. When all the dimensional elements required are carried in, we provide the general contractor with an analysis of these elements over time. In this particular case, we analyzed 4 3D models that we received from the architects, and for each of one of them, we summed up the analysis in a file that included all the changes brought to all types of facade and all the areas of the building. Moreover, this analysis enabled us to check whether the architect had actually made the required optimization. Another possible use of BIM is in surface optimization. Our team designed the so-called shelves that were sent to us by the architect in 3D file. We realized upon receiving the files that, in order to build those shells, we will have needed more than 300 different molds. That would have been impossible to do that within budget. We started by analyzing the geometry, taking into account surface and height limitations, but also by looking how the architects had designed the curve. As a result of those analyses, we realized that it could be simplified and boiled down to 5 sections: a straight line, a curve, a straight line, another curve, and another straight line. On the basis of this principle, we managed to develop 3/4 of the shells in the stadium just by using 8 basic shapes, i.e. cone, cylinders, tori, and planes. We managed to bring the number of different molds down to 26 for the whole shell. In order to understand optimization, we brought to the architect design in full respect of their style. You can see here in white the architect's original drawing, and in color the proposal designed by our team. There is a maximum difference of 11 centimeters between the two designs. More importantly, BIM was used in the Arena Stadium project to design the tiered seating section and to control the visibility curve. We analyzed the architect cross-section blueprint with the 3D software. We adjusted the seating and the software by taking into account all of the elements of information about the curve in order to obtain the required coefficients. By analyzing the visibility curve with the modeled cross-section, we realized that were 21 out of the 50 rows of seats for which the visibility had not been verified. In other words, out of a total of 31,700 seats, 9,500 had not been verified. So, we redesigned the tiered seating based on the 3D model, into which we integrated all of the relevant data we got from the contractor, the architects, and the client. After this reconsolidation, we chose to design the seats and the precast tiers as a whole because we realized, when analyzing the architect cross-section, that the prefabricated beams required millimeter accuracy, which was not compatible with the precast material. We did two things: redesign the tiered seating to ensure a proper visibility curve, and optimize the fabricated beams with the centimeter accuracy. After that, we created a software to check and correct our work on the basis of the 3D model. The operator runs the software to check the position of the graded seating on every cross-section. This is something we create to verify the data we enter into the model and make sure there were not human errors made by the operator. The operator starts checking from the trial line of the field, and the software confirms the result for every 50 seats, and so on for the 31,700 seats. We also used BIM to check the visibility for every seat on every row. The operator figures out the best position for every viewer, and the system draws 4 lines for there to every corner of the stadium to make sure nothing interferes with their vision, in particular one of the supporting pillars for the roof. The computer checks every single visibility line and verifies nothing interferes with it. If anything blocks the visibility line, it will light up in blue. This allows us to know which seats exactly have existing elements interfering with their visibility line. The system checks every single seat's visibility and removes all seats with no clashes, i.e. with clear visibility. The seats with blocked visibility because of interfering elements light up in red in the system. We can translate that back into a 2D blueprint with every single seat identified. Working with BIM is more than just a 3D drawing, because it's a comprehensive integrated model. It requires processing information and analyzing it. We apply our skills in building synthesis to the software. This means that when drawing the tiered seatings, the seats, and the concrete shells, we will do so by integrating all the building's constraints, the structure, the freeways, and all of the other standards, because our work is to make everything work together, so that when we hand over the final 3D model, it has been analyzed geometrically and can be implemented in the shop drawing phase. We hand over to the project managers a 2D file includes all clashes as well as the analysis required for the technical and architectural integration. A technical synthesis will show, for example, what you can see here, which is the analysis of the underground networks, with the clash between the different elements. Likewise, with the architectural synthesis, whenever we detect a problem, we identify it and suggest a solution whenever possible. You have just seen the model for the Arena Stadium in its construction phase, including all elements analyzed and synthesized, as well as some of the possible applications of BIM.